Now that we've provided energy into the atmosphere, we're going to talk a little bit about temperatures. Most of you might be kind of interested in temperatures. At least I want to know what kind of clothes I need to wear as far as temperatures go outside. Can I go in shorts, or do I need a big heavy jacket? So they're kind of things that most of us think about when we think about the weather. One of them is obviously temperature. So how do we get the temperatures we get? Why is temperature different days, or the same over several days? Why did it get colder at night than it did why is the daytime the hot time? All questions we're going to talk about this week. So I just wanted to start simple weather map. You've read them now, you've looked at them. These are all surface weather map, very station symbols. See a lot of temperatures in the 70s. Man, there's a large area of the country. Temperatures in the 70s. Then there's this stationary front. Temperatures are in the upper 80s, even right around 90 just south of it. There are actually some 90s there. That's a stationary front with cooler air to the north, warmer air to the south. And notice the winds are kind of parallel to the front there. Interestingly, right now along the East Coast, we're getting a lot of east wind off the ocean. If you go look out over the ocean, ocean water temperatures are in the mid to upper 70s out in this area right now. The Gulf Stream in the 80s. What do we have back here over land? Mid to upper 70s. This is all due to the influence of the air coming in off the water. Get further away from the water, get some more sunshine, and it gets a little warmer, a little better. Temperatures in upper 70s or maybe even higher. So you can see the influence of where we live. If you look at West Virginia, notice Beckley is 70 degrees. Yet over in Huntington, it's 77. Well, why is there a 7-degree difference in that distance? Elevation. You're higher up at Beckley than you are in Huntington. So there's a difference due to elevation in temperatures. I also wanted to show you Beckley as far as a 1 day, or 3 days actually, meteogram. You're going to see meteograms this week in some of your labs. Temperature, light blue curve. Dew point down here, and relative humidity in between. We're not worried about relative humidity right now, but we're kind of worried about temperature. So during the day, the temperature is fairly warm. Notice it was in the mid 75 degrees here. At night, temperature is down to 62, 56. It dropped off pretty quick, didn't it? Then it went back up again into the 70s. Back down some, not as much. 64, back up. Bet this was a very more sunny day, almost 80 degrees right there. And cooled off again, back down to all the way down to 57 there. So, what caused that temperature variation? And why is one day just slightly cooler than another? So, let's explore some of that a little bit. Let's look through some of it and see if we can come up with some reasons for what is happening with temperatures. So I wanted to use this slideshow to go through some temperatures and beginning just a little bit of how they impact the atmosphere. So with this, we're going to talk about the heat. Heat is just temperatures, energy, and motion. So what causes that heat transfer? Well, when we look at temperature, temperature is the kinetic energy of a molecule. All molecules, the atmosphere, the earth, solid, liquid, molecules move. The faster they move, the higher the temperature. So now that we know that, if we measure a high temperature, we know the molecules are moving faster. If we measure a low temperature, they're moving slower. And to make the molecules move faster or slower, we transfer heat or energy out of the molecule. That kinetic energy is going to move. And it always goes from warmer objects to colder objects. So that is the process that heat transfers. So examples of how we can change your temperature. One of them is a temperature gradient. Say you lived in, we'll just use Beckley because that's where your university is located at. And the temperature in Huntington just had a cold front go through, and it's 32 degrees in Huntington right now. Temperature at Beckley currently is Beckley and Huntington. So as that temperature gradient passes you, what is going to happen is your temperature, there's been a heat transfer out of your area. The hot air is being transferred away. Cold air is rushing in. You're going to get colder. So that is what happens as temperature advex moves into your area. And everywhere there are temperature gradients, some extreme like that, others very minimal. But if you know which direction the wind's blowing, that is the direction that's advecting where the air is coming from towards you. If at the same token I had winds blowing in Beckley out of the southeast, and Huntington's winds, while they may have been 32, but if the winds were out of the south, that cold air is not coming to Beckley. It would be going away from Beckley. Warmer air would be moving into Beckley. Warmer air would be probably coming into Huntington as well. So you wind up changing both temperatures. There are ways heat flows in the atmosphere through radiation. We learned a lot about that in the last chapter. Conduction, convection, and latent heat. Latent heat is all due to phase changes in water. Water is the only element in the atmosphere that changes phase. Phase changes means we go from a gas to a liquid to a solid or back. So what is well, we talked about radiation. It just moves energy through a vacuum or space. And the sun is our source of radiation. The earth through the greenhouse effect and all also provides some warmth. Conduction. You ever put your hand on a hot surface and immediately move it away? That is conduction. The kinetic energy is moving, literally hitting your hand from the hot surface back into your hand, making your hand hotter, burning it. If you're down at the beach sometime, ever go to walk across the hot sands during the afternoon on your feet? I love to watch people out at the ocean front that will take their shoes off as they're leaving the boardwalk to walk down to the ocean front. And it's a good about 50 to 75 feet to really where you want to get down by the water at Virginia Beach oceanfront. If the temperature is in the upper 80s, it's had direct sunlight all day, that sand heats up a lot. So what happens is that person's foot, as they walk off the boardwalk where the concrete, nice and white, is, all of a sudden they're hitting that dry sand and their feet are burning. I can watch people run, probably the fastest they've ever run, to try to get to the ocean to cool off their feet. That is conduction. Convection. Convection happens in liquids and gases. It does not happen in a solid. Atmosphere is a gas, so it does happen. What happens is you heat the air at the surface. The air begins to rise up. It cools because the atmosphere in the troposphere cools as it's rising and then sinks back down to the ground again, that cooler air, and just creates a big circle. You see the evidence of that sometimes if you were a glider pilot looking for thermals, or ever watch a bird just go up and up and up around in a circle over one area without ever flapping its wings. That's convection, pushing the air up in that area. Somewhere outside of that area, the air is coming down. That bird ain't going to go there because it doesn't want to have to work. Now, phase change. So, let's think about this for a minute. We have a vapor. a water vapor. That's a gas. A gas is going to be moving its molecules more than a liquid, and the liquid is going to move them more than a solid. So if I want to go from a gas to a liquid, I am releasing heat. I'm getting rid of some heat into the atmosphere because of that change in phase. So literally, when we form a cloud, heat is released into the atmosphere. Now, if I continue on down and go all the way down to a snowflake, more heat has been released into the atmosphere. So you see, when I'm forming clouds or forming precipitation, the atmosphere is actually getting heat, latent heat, from this process. Now, let's go the opposite. I melted it. I'm back into a liquid. In order to do that, it had to gain some energy. So it had to receive some heat. So if I'm melting an object, heat is being absorbed by the liquid, or the atmosphere is losing heat. If I go from a liquid to a gas, get rid of the clouds, they're dissipating. Again, I'm absorbing heat. It's getting cooler. You ever see this with evaporation? Sometimes on you have a wet object and wind hits it. You'll notice that the hand that's getting hit by the wind, the part of that hand is getting cooler because of evaporation. It's taking the liquid that's on your hand and turning it into a vapor. And the water holds a lot of energy. It takes a lot of energy to heat up water. My example, again, the Atlantic Ocean here near me, the water temperatures in the winters get down into the 40s, maybe even mid 40s. Sometimes I've seen it as cold as the upper 30s, but generally we'll talk the mid 40s. Water temperatures during the summer get up close to 80, maybe mid to upper 70s more likely. But remember, the sun started to come back literally beginning of December, middle of December, the end of December there. So the sun's coming back, it's beginning to heat. It takes until June to mid-July, late July usually, before we start reaching significantly warm water. And July and August are the warmest. It has taken all that thermal energy that long to finally heat up the water. It takes a lot of energy to heat water. Now, land is a whole different story. I used to love to go to Kansas training in the spring because I knew it was going to be warmer there than it was near the oceans. Why is that? Because the land absorbs heat much quicker. It warms up. Yes, it can be more extreme. And I can get some cool days in the spring, as I know. But a lot of times there'll be some warmer weather in the Midwest than before it gets to the coastline. Here's just the confusion of all that energy that came from the sun. What did it do? Well, it reflected. It scattered off of clouds, reflected off the earth. It was absorbed by the atmosphere. Some of it was absorbed in long-range radiation. Greenhouse gases picked up some of that. The infrared coming back from the earth. All of this has to be taken into account to come up with why our temperatures exist like they do. So, conduction and convection can be measured together. And they are sensible heating. They form the cumulus clouds. They produce changes in temperature. And here is all that radiation we saw. Notice there's a big surplus of radiation down back by the equator, out up over 30 degrees or so north. There's more energy received there than there actually is temperature to support that. However, if you look away towards the poles, there's a deficit of the amount of radiation compared to the actual temperature. So what we actually get is there must be a way that warmth that's getting put in down by the equator is getting shifted to the north and the south. And that is through air masses Storms, ocean currents, tropical storms are one of the biggest transport energy. So what are air masses? Well, they're uniform areas that have similar temperatures. If I put a bunch of air across Canada right now and told you that air was going to be sitting there for the next week, not moving, high pressure, very little motion, what would the temperatures of that air be like? Well, let's see. There's some snow in parts of that area right now already. There's not a lot of water up there, so I would think it's going to be kind of cool, maybe even cold and dry. And that is an air mass. It has become cold and dry. If it did it in the tropics, over the ocean, it would be warm, humid. So these are air masses, and where they come together are the fronts. So now you've just seen an example of how that energy is being transported by these air masses. So this is what triggers the weather. Interestingly, we all wonder, you got asked the question in the first week of course, why is it warmer during the day than at night? Why isn't it warmest at noon instead of in the afternoon? It's warmer still. The reason is, you look about it, the sun's energy starts up about 6 a.m. The Earth, at the same time, is releasing infrared radiation, but there's more sun energy coming in than there is the infrared radiation going out at that point. Temperature is going to rise. Eventually, they're going to cross. When they do, it's going to start cooling again. And you'll notice that that is in the afternoon. Yes, the peak of the solar radiation occurs at noon, but by afternoon is when it takes to get the infrared radiation to be stronger than the solar radiation. Surface cover plays a big impact on temperature. Think about in the wintertime. You just had a fresh snowstorm go through. Everything is really nice, bright. Sun doesn't strikes that snow, and you need sunglasses. It's very bright out. Why? Because the snow is reflecting a lot of energy back out into space. All that sun's energy is getting taken back out into space. So what happens is it doesn't get nearly as cold, or nearly as warm. Excuse me. It does get cold. It stays colder. The same thing happens if you've had a lot of rain. You want to heat up the ground and your air. But what happens is the air, all that moisture is being evaporated. The ground's not able to warm up as fast. It stays a little cooler. All factors to consider when you're looking at your local temperature. And here is an urban heat island. Again, thinking about how temperatures are impacted with that. Lots of concrete, lots of buildings drawing in heat. Sometimes they can be a lot warmer downtown than outside in the country. So let me know if you have any questions.